Hello everyone, and welcome back to this tutorial series on the theory of computation. In this video, we'll be discussing the closure properties of regular languages. But before we get right into that, I want to review the notion of regular languages and the concepts of DFAs and NFAs, but rather quickly. So you'll remember that when we started this journey of theoretical computer science, we introduced the very first computational model or model of computation, which was the DFA, right? So the DFA, or deterministic finite automata, is some machine M that takes as input a string and then returns either accept or reject, right? And so we then used this model of computation to define a family of languages that we called regular languages. And so a language is regular if there exists a DFA-M that accepts it. And so you'll remember that the definition for languages accepted by DFAs consisted of all of the strings that start at the initial state of the DFA, and then once the machine M processes the string, this leads the machine to enter a final state, right? And once we defined the family of regular languages with DFAs, we moved on to this other computational model, the NFAs. So in the NFAs, we introduced the notion of non-determinism, of having a choice in the transition function. And we actually saw that the computational power of NFAs equals the one of DFAs. And so the family of languages accepted by NFAs, right? We saw that the family of languages accepted by NFAs is exactly the same as the family of languages accepted by DFAs, okay? And then as a corollary to that, we saw that then to prove that a language is regular, we need only show that there is an FA, so an FA which can either be a DFA or an NFA, M that accepts it, okay? And so, right, the main result of that was that to prove L to prove L to be, well, to prove that L is regular, we need only construct an FA, which can either be a DFA or an NFA, okay? And so now that we've seen that, the next question that we might have is, okay, let's say I have two regular languages, let's say L1 and L2. If I combine these regular languages in a certain way, for instance, I take the union of these two languages, right? And these two languages are regular. Does this necessarily mean for any pair of regular languages that the union of these two regular languages is also regular, right? So will this always be regular? Okay, and so why do we care about that? Well, if we can show that for any pair of regular languages, when we take the union, we get another regular language, then that allows us to build up from smaller languages, bigger languages. And so smaller and bigger should be in air quotes, right? But this kind of allows you to show that a language is regular without actually having to construct, say, another FA, okay? So what I mean by that is, so the motivation here is, suppose we have the alphabet AB, and we have one language which is AN, so any number of A's where N is even, okay? And then we have the language L2, which is any number of B's where N is odd, okay? And now we know that these two languages are regular, right? We can build DFAs or NFAs that accept both of these languages, right? Okay. But now the next question is L1 union L2 regular? Okay. So if we know that both of these languages are regular, do we actually need to bother with constructing a new NFA or DFA to accept this union of two languages? Or can we just state, oh, well, because I know that both of these languages are regular and we're taking the union, then this will automatically be regular, right? If we can do that, then that saves us a lot of time in proving things, right? And so that's the motivation to discussing what we're going to be talking about in this slide, which is closure properties, okay? And so we have a more abstract definition, and then we can talk about some specifics. So the abstract definition here just says that if we have two pairs, let's say a pair of regular languages, L1 and L2, and we have theta some operation, right? Some operation. So theta is some operation, some language operation. For example, the union, the intersection, or we can create any other operation, right? We can think of taking the first letter of a string, taking the last letter of a string, and then swapping them, right? That could be an operation, right? So that could be the swap operation that I just invented, okay? So suppose we have some operation, some language operation. So I should specify that this is a language operation or operator. And we have two regular languages, right? Then if for any pair of regular languages, L1, L2, L1 theta L2 is regular, then we say that regular languages are closed under the theta operation. So then, for example, if we were talking about the union, and we could show that for any pair of regular languages, once we take the union, this union of regular languages is also regular, then we would say that, if we could prove this, right, that regular languages are closed under the union. Okay? And so that's what we mean by closure properties. Okay? And now we have the following result. Okay? We have the following result that says that for any pair of regular languages, L1, L2, okay, the union of these regular languages will also be regular. And this is for any pair of regular languages. Okay? And so at first this might seem surprising because maybe if we combine languages in such a way, using their union, maybe we can get something that an NFA could never actually recognize, or that a DFA could never actually recognize. But this result shows us that that's impossible, that if we have two languages which are regular, okay, and we take their union, or we take their concatenation, right, in either case, we'll always be able to create a new FA to accept this language, okay? And the same thing is true for unary operators. For instance, the star operator, okay, is closed under, regular languages. So then this would mean that regular languages are closed under the star operator, right? That's what this would be. And then the same thing here, we would say that regular languages are closed under the complement, okay? So this was the definition, and I should have probably separated this better, but this is some results, right? Some results. Now, you might be thinking, okay, so you've just kind of given us the definition and then stated some results without proof. And so what we're going to do now, right, is we're going to have to prove this. And the typical strategy, right, so the strategy of proving closure properties is the following. We're going to use a proof by construction, okay? So we're going to use a proof by construction. So, for instance, for the union, I'm going to say pick any two arbitrary regular languages, L1 and L2. Because these languages are regular, that means that there exists DFAs, M1 and M2, such that the language accepted by M1 is equal to L1, and the language accepted by M2 is equal to L2, right? This we know by definition. We know this by definition. Okay? And then the strategy is we need to construct, right? We need to construct a new machine, a new FA M prime from these two smaller machines, from M1 and M2, right? From M1 and M2, right? Such that this new machine accepts exactly the union of the languages, such that the language accepted by M prime is equal to L1 union L2. Okay, this is the strategy, right? In fact, if I create a new page here, that's only part of the strategy, okay? So in this proof by construction, the first part, okay, is actually the construction of the FA M prime, right? So, for example, in our case here, that's when we create a new FA M prime, which is based on M1 and M2 in some way, right? I'm still talking really abstractly, so if you're still a bit confused, that's fine, because it's still at a very high level. But just imagine that I'm creating M prime based on the components, on the mechanics of M1 and M2, right? And so I've built this machine in such a way that it accepts the union, okay? So that's the construction of the FA M prime. Then the second and probably most important part is to prove the correctness. Prove the correctness of the FA M prime, right? That is, we want to actually prove that this statement is true, okay? And so here, this is a set equality, right? And so hopefully you remember that to prove a set equality, you need a double subset inclusion proof. And so what you'll need to do is you'll need to show that if you take any string that's accepted by the machine M prime, then it actually belongs to the union of the languages. And if you take any string that belongs to the union of the languages, then it will be accepted by this new machine M prime, okay? But typically in the proofs that we'll see, the second part, right, this second component, part of it is implied in the construction, okay? And then part of it is also skipped, okay? So you're going to see that in the exercises that I go through, I will discuss one, and typically partially or completely skip two. That isn't to say that 2 isn't important. In fact, I think 2 is probably the most important part of the proof, because if you have some statement that you're claiming about the construction of your machine, you need some proof to back it up, right? You need some proof to guarantee that that's in fact what your construction does. But What I'll do instead, so to substitute 2, I'll just give some intuitive argument. Right, so I will give some intuition. But definitely beware of this, right? So beware, because depending on how you're taking this, if you're taking this class formally, maybe you have an assignment, and maybe it actually says to prove the correctness of the FA, in which case, don't just give an intuition, you actually have to do something like this, okay? But just be aware of this, that in the proof by constructions that I'll give, some of them or most of them might be incomplete because I won't have given the full correctness proof, okay?